Good evening, ladies and gentlemen. How's everyone tonight on this absolutely superb evening? Not too bad out there, huh? Good. All right, well, thanks for coming tonight. Launching in August 2007 for arrival in late May 2008, the Phoenix mission to Mars will bring 11 science experiments to explore the northern near-polar environment on Mars. The spacecraft's landing site is between 65 and 72 degrees north, analogous to central Greenland and Alaska. And like Alaska, the Martian Arctic plains have permafrost. This ice may have melted and refrozen over millions of years, making this a location that might have been suitable for life. While Phoenix is not a life detection mission, its objectives are to understand how water and ice at the landing location have interacted with the soils over time, and to understand if the environment is or could have been compatible with life. A physicist at the Jet Propulsion Laboratory, tonight's speaker has, at various times, worked on semiconductor surface and interface science, planetary science, microelectric mechanical systems, and scientific instrument development. One of the highlights of his career at JPL was his service as project manager for the Mars Environmental Compatibility Assessment, a soil analysis payload intended to fly on the canceled Mars Surveyor Program 2001 lander. He has designed, built, and operated numerous laboratory instruments for materials analysis, a field in which he has published extensively, and was also the first recipient of JPL's Lou Allen Award for Excellence. Currently, he is a co-investigator responsible for the Microscopy, Electrochemistry, and Conductivity Analyzer, which is a soil analysis instrument on the Phoenix mission. Ladies and gentlemen, please join me in welcoming tonight's guest, Dr. Michael Hecht.
Laser pointer? The laser pointer? Oh, yeah, right here. Am I on?
You're on.
Do I have sound?
Do we have audio? There you go, the green laser pointer.
I didn't hear anybody. We have audio. We have ignition. We have an unresumed slideshow. Okay, that was the talk, so if there's any question. It is great to be here. It really is a delight for a number of reasons. First of all, this is why we do this. This is why we go to Mars. It's not just to tell stories to 1,000 of our colleagues in planetary science, but it's to share the excitement with the world. And I like nothing better than to speaking to folks who aren't those same old 1,000 faces I see at all the conferences. So welcome, especially those of you who don't work here. And again, I know I see mostly unfamiliar faces, and that's great. Where to begin? This is also a very exciting time. It's very exciting to see all you folks here because that means Phoenix has arrived. I've been here 25 years. And when I came here, Viking had ended a couple of years earlier, our last mission to Mars. There was nothing. It would be 15 years before we landed again on Mars. We were thinking Magellan going to Venus. We were thinking farther off, Galileo, Jupiter, Cassini, Saturn. And that was about it for the planet, exploring the planets. A mission a decade maybe, or in one time, and it was becoming a bit more. And with all our complaining about funding and this and that goes on here, of course, the fact that we have to get in line behind all the other missions for publicity and for filling a room is just the most wonderful thing. You know, that we've got MER up there, we've got Odyssey still taking data, the beautiful new data, new science coming down from MRO, looking forward to MSL, and we have to get in line. I couldn't ask for anything more than that. So thank you for the kickoff of our turn in the limelight. Phoenix Mars Lander 2007, and yes, we had that logo before Firefox. Okay, so let me make this annoying thing go away. I made it go away. There we go. Okay, so I'm going to try to just tell a few stories here and make it not terribly technical. I want to tell you a little bit about Mars, a brief history. Just so you know what we're talking about, why we're going. I find it a fascinating place, and that's why I'm doing this. Tell you a little bit about Phoenix, the pieces, how they fit together, what they're doing, and what the overall goals are. I want to tell a little bit of a story about our quest for a place to land. Where should we go on our summer vacation? Because as you already heard, we are going way, way up north. We only have solar panels to power our mission, so if there's no sunlight, if it's not summer, we're not going. So this is our summer vacation. That's why we're going up north and not down south. And I thought I'd talk a little bit. I always like to give a little bit of a feel of what it's like to, to be involved in developing these things, just what the life is of a scientist/engineer trying to put something on another planet. And so I thought I'd talk a little bit on the aspect of why do these things cost hundreds of millions of dollars. It's an enormously exciting, constant adrenaline rush for 4 years. Interesting times, and I'll try to give you a little flavor of that. Okay. All right, so what location, location, location. That tells you a little bit about what Mars is like, what any planet is like. You see here a chart of the temperatures of the planets, the pressure on the planets, and Earth is sitting there obviously at about 1 bar. Why is it 1? Because that's how we decided it would be a bar. And we're sitting there at temperatures that are kind of a balmy, sort of between 0 and a really hot day, maybe 50 C. Pleasant place, just about the right amount of gravity, of course. Mars is sitting down here. It's farther from the sun, about half again farther from the sun. So, of course, it doesn't get as much sunlight. It's a bit chillier. Maybe minus 40 might be an average temperature. But it does get, on a warm day in Mars in the summer, the temperatures of the ground will get above 0. So it's not an entirely unfriendly place. A warm day in Mars is a very cold day on Earth in the right locations and the right time of year. It's smaller than the Earth, as you can see. It has about 3/8 the gravity, so you'd be your step would be indeed very light on Mars. And unfortunately for visitors, for potential visitors, it doesn't have a lot to breathe. It's about 1% of the atmosphere of Mars, a very, very thin air. You think about what happens when we go up to the top of a mountain, the air gets thin and it gets chilly, except when we're in the sun, you can get very hot because there's not much air to move the heat around and to cool you off. Go, really, really go to a mountain that's at 100,000 feet, and that's more what Mars would be like. But there is air. There's enough CO2 to, there's 30 times more CO2 than you would find on Earth. A lot of carbon dioxide, only just a smidgen of oxygen. So it's a different sort of place. And we know if you just look through a modest, inexpensive telescope at Mars in the sky, you see little white patches at the top and bottom. You can see a little white patch down there. It has polar caps. We've known this for years. We've known for a long time that there's lots and lots of water on Mars. So what's all this about water? Why are we so obsessed with, is there water on Mars? And sometimes you see headlines, someone finds signs of water on Mars. Well, the truth is Mars is one great big cold desert. If you hear people say water isn't stable on Mars, that's not true. Water is not any different on Mars than it is on Earth. The problem is it is a desert. Now, what's a desert? It's a place where it doesn't rain, it doesn't snow, where there's no rivers flowing. There's nothing to move the water around. So if there ever was a little puddle of water down there at the equator, it's long since evaporated and gone up to join all of its cousins down on the polar cap on the south or the north. And it just is a cold place where there's ice in one place and dry stuff everywhere else. So that's Mars. And we are also obsessed with water because we all believe that if you're looking for life elsewhere in the solar system or in the universe, a signature will be water, liquid water. So the quest is really about liquid water. Could there be liquid water on Mars? Yes, it gets warm enough. There's plenty of ice, but there's nothing to move it around. What else can I say about Mars? The weather, there's not a lot of air, but the wind can blow pretty briskly. If you were standing on Mars, you wouldn't get very much cooled or heated by the wind, but there'd actually be a lot of evaporative cooling. Your sweat would work very effectively to cool you off. You'd get a lot of heat from the sun in the sunlight, and you'd lose a lot of heat to the sky if you were in the shade. You might use an umbrella to keep warm, to keep the sky from sucking all your heat out. That's a concept we don't think about much on Earth unless there's any amateur astronomers here. Anyone who uses telescopes? Do you ever put a dew shield on the top of your telescope? Yeah, it's just a ring of black paper to keep the lens from getting cold by radiating to the sky. We hardly ever think about that on Earth, the fact that looking at that cold sky sucks the heat out. On Mars, it's an enormous factor. So everything's a little different. It's like, I sometimes say it's like looking at Earth through a funhouse mirror. If you look at Mars up close, you see lots of enormous riverbeds, ancient riverbeds, and they came from billions of years ago when it's pretty apparent, I think almost everyone in the business is in agreement that there was rapidly rushing water on an enormous scale, flooding parts of Mars billions of years ago. Modern times, there's hints that water is still important. There's what we might call Peri-Glacial terrain. Terrain that looks like it's broken up by stuff freezing and either thawing or evaporating over thousands and thousands of years. And more recently, there's a lot of things that look like little gullies where water might have flowed. But we haven't found anything like vent holes or steam coming out or anything that indicates that there's another reason you don't have deserts on Earth, because you have heat coming out of the ground that's creating liquid water and geysers and things. We don't find things like that on Mars. It's kind of unfortunately, a pretty kind of staid and uneventful place today as far as water goes. And the other thing I'll say about Mars, because it's certainly a very current and relevant topic, is that Mars suffers, as does Earth, from global climate change. And for many of the same reasons, for most of the same reasons. Now, obviously, industrial production of CO2 is not one of them. But the changes in the orbit over time, just like Earth's orbit changes over tens of thousands of years, Mars does even more so. And so, while right now the North Pole of Mars might have relatively cool, long summers, in 25,000 years it will have relatively hot, short summers. Same thing happens on Earth. We have CO2 that goes up as a greenhouse gas during parts of the year and comes down to the surface during parts of the year, and that changes over time. We have dust that spreads over large areas and makes what was shiny ice a very absorbing material, and vice versa. As more ice comes down, it becomes more reflective. Just like on Earth, it changes the heat balance. The more ice you have, the colder it gets on Earth. The more dust you have, the warmer it gets. Same thing on Mars. So that's one of the other reasons, other than life, that we're interested in studying Mars, because it will tell us about climate change on Earth. So that's a bit of background. Okay, so there's Phoenix. That's obviously an artist's conception, and you see this long arm here digging a hole. That arm has been in development in various incarnations for maybe 15 years. We've spent, I don't know how, probably $20, $25 million on it. And what it does is it digs a little hole like that if you give it a week or two. Now, yes, I know that any of your 2-year-olds could do this with 15 minutes of instruction. But I like to point that out because we make a great deal out of our robotics, and we should never forget that our most sophisticated and expensive robots are still very, very limited in what they do compared to our 2-year-olds. We'll get there, but there's a lot to do. Then there's this tunnel vision mantra at headquarters about what Mars is about, the Mars program is about. It's about follow the water. And they've been saying that for years, follow the water. Why? Water tells us about life. Water tells us is about climate. Water even tells us about geology, the kind of rocks that the MER mission finds. And they analyze. They analyze in terms of, was this rock ever in water? Could it have existed if it was in water? That water shapes geology on Earth and maybe on Mars. And finally, if we ever hope to send humans to Mars, and I would love to see that day, we will need to understand what water does on Mars. So that's the common uniting theme. Now, why go where we're going, way up north to, well, originally where that arrow is, that dark blue arrow? This is an interesting map. It's a map taken by the Odyssey spacecraft, part of the gamma ray spectrometer suite of instruments that's been flying since, I've lost track. It's been up there for years. Sorry? 2001, that's right, of course. I knew that because it goes with the 2001 lander. When originally this map came out, this is a map of subsurface ice, and originally I remember it came out, all the dry parts were blue and all the water parts were yellow, and it didn't take too long before people figured out that was confusing. So now we have maps where all the blue stuff is water and all the green and yellow stuff is dry. But this isn't, again, liquid water. This is ice underneath the surface, and we see it by looking at, if you will, the reflected cosmic rays that come off the surface that are, particularly the neutrons that are absorbed by water. And what this is showing is that under the ground, and not very far under the ground, inches under the ground, there's ice everywhere. This is like permafrost you'd find in Siberia or in the Antarctic dry valleys, everywhere. And as I mentioned up here, this was predicted by Actually, Bruce Murray, who's at Caltech, was a professor at Caltech, was the director of the Jet Propulsion Lab for a number of years. Way back in '66, they looked at some simple facts about Mars, how much water vapor seemed to be in the atmosphere, what the temperatures were, and said, everywhere north of about 50 degrees and south of about 50 degrees, there should be ice under the ground. And through three decades later, indeed, there it was. So everywhere we've gone on Mars, so far, that we've gone successfully and landed has been down in here. We say, follow the water, and then we go to the desert, every time. So the Phoenix mission, our grand purpose is to go somewhere where, while there may not be liquid water, at least there is ice. And we can say, all right, was this ice ever liquid? How does icy soil differ from dry soil? Because even on Earth, icy soil does interesting things. Even things sometimes live in icy soil. So we want to actually go there. The Polar Lander mission tried to go to the South Pole back in '99, and I think probably most of you know we didn't quite make it. We made it very close. We got within a few inches of the surface, and then everything went wrong. So haven't heard from it again since. We keep listening from time to time. But we want to go back. In this case, just the way the planets line up tell us that we should go to the north and not the south. And originally we thought we'd go to one of these really dark blue areas because that's where there's ice really close to the surface. So why Phoenix? Why is this thing called Phoenix? Because it confuses the heck out of everybody since it's being led by the University of Arizona. And who knows where the University of Arizona is? Somebody. It's in Tucson. So we're constantly telling our travel people, I need to go to the Phoenix meeting in Tucson. Can you get me plane tickets? And we never know where we're going to go. But it was called Phoenix because of the mythical Phoenix that, of course, rose from the ashes, from the fire, or as I said here, rising from the fire to study the water. It was rising from the ashes of this 1998 Polar Lander mission that sadly crashed on the surface, and the 2001 Mars Surveyor lander that was the companion piece to the Odyssey orbiter. They were both supposed to launch at once, but when this one crashed, these two things, if you kind of forget about these funky angles on the solar panels, they look kind of similar, and they are. They're very similar. So when this one crashed, we said, whoa, let's wait a minute before we send this one and think about whether we're doing the right thing. And as a result, this is like the end of Raiders of the Lost Ark. This thing got put in a box in a warehouse where it was being studied by top men. For years. And when we had an opportunity to propose a mission, a so-called low-cost mission between $300 and $400 million, we said we can't build a lander for that, but we just happen to have one in a box we can use. So out of the ashes of this lander that was sitting in a box, some of the instruments, including the one I'm responsible for, that was built for this lander, never flown, and some of the instruments on this lander that, of course, crashed, but there are designs, there are spares. We can build it better. We have a $6 million instrument. We can rebuild it and make it better than ever. We put those things together to propose a mission to go study this icy soil. You notice it doesn't have wheels. It's amazing that people are surprised when a spacecraft doesn't have wheels because when we did Pathfinder, people were astonished that it did. And now people expect it. But the reason it doesn't is we expect this icy stuff to be absolutely everywhere. And the important thing for us is going down, not going over here or over there, but digging down here. So we don't have wheels. Wheels are expensive too. So what are we going to do? Well, first of all, this is a short mission because when the sun goes away, as we get late into the northern polar summer, our power goes away. And no, we cannot survive the winter and turn it on next winter. And by the way, the winter is, a Mars year is about 22 months. It's almost 2 Earth years. So that's a very long winter. A Martian day is just a tad longer than an Earth day. It's about 24.5 hours. You get an extra half hour, which is nightmarish for people that are running these missions because every day you lose half an hour of sleep and you find yourself having breakfast at 3 in the afternoon pretty soon. But we'll have just a few months. We'll just have 90 days, maybe 120 to do this mission. So we have rather modest objectives. We want to get to that ice. We want to dig it up, get to it, study it, and try to understand, well, we expected since 1966, expected it to be there. We don't know exactly how it got there. We expect it to be there because it's like back in the days before they before you had self-defrosting freezers. You know water would end up in the freezer coils because it's a nice cold place and there's water around. The only reason we expect it to be there is because it's a cold place and there's water vapor around. But that doesn't say whether it just got there by water molecules diffusing in, or whether it got there because it snowed, 30,000 years ago, or whether there was once a lake there. We don't know any of those things. So we want to understand how it got there. We want to ask whether, with all this global climate change, it was ever liquid, which would be really exciting. We're looking for clues that it might have been. We want to study this balmy summer climate. It's still, an average of minus 40 degrees, but as Mars goes, it's a balmy summer climate. And we want to ask whether the environment we're digging in, this icy soil, could support life. We're not asking if there's life there or if there was life there. We're asking if the raw ingredients are there, starting with, might there have been liquid water? Might there be chemicals that would provide nutrients for anything living there? Is there anything really toxic to life there? Study that environment just to ask, is this the kind of place a future mission might actually go to look for signs that something might have been living there? So, of course, we load up this deck with as many instruments as can fit. We have this cute little camera. I always thought it looked like a little smiley face there, and it nods up and down, and it's got little sort of eyelids that open and close. This is the workhorse, this robot arm. There's a camera in the end, and there's a scoop on the end. The camera's there so we can look at the dirt we just dug up. And this arm, in addition to taking pictures, digs up dirt, digs a trench, and puts the dirt into the various instruments to study the soil. So this will dig, pick it up, pour it into the slot, and then let this instrument, this Tega instrument, do its thing. So there are two soil instruments. There's something called Tega and Mecha. I'll tell you what they stand for in a moment. There's the robot arm, the RA, because we JPLers can't speak without acronyms. TLA, as we call them, three-letter acronyms. And the MET mass, MET is short for meteorology. It's what we use to study weather with. Now, one of the things that you probably know if you have a home weather station, you can't put it too close to anything. If it's right by the side of your house, the house gets in the way and changes the wind and changes the temperature. So you always put these instruments up on a little mast to get them out of the way of all the stuff down in the lander. So we have a MET mast to measure pressure and temperature. Something called a LIDAR. LIDAR is like radar. It is an acronym, but it's not usually capitalized. Radar is an acronym. It's not usually capitalized. And it's essentially a version of radar that uses laser beams. So it shoots a laser beam up in the air, looks for the blip, the echo that comes back, just the way that radar and sonar do, looks for the blip that comes back, and it tells it, and by measuring that very short timing, and you can learn about what it's scattered off of. In this case, we're interested in clouds, because yes, Mars does have clouds, little ice clouds and that float by, and it's a very important part of atmospheric science. I think they tend to be fluffy pink clouds, fluffy blue clouds against a pink sky, something like that. I think that's what it is. So it would certainly look alien if you woke up there someday, like Edgar Rice Burroughs might have described. What else have we got? I think that's it for the instruments, except the ones not shown. There's an instrument on the side of this robot arm scoop that gets stuck into the soil that I'll describe. And then there's this thing called MARTI, the Mars Descent Imager, and that's hiding underneath because it's going to take pictures as we land, and then it's going to end up on the bottom of everything when we get on the surface. Oh, I think I did this. Did I just go backwards? Yeah, I did. Son of a gun. Okay, well, we talked about this because I'm going backwards again. Man, how do we do this? That'll do. Okay, there we go. The arm, robot arm. This robot arm this is actually how long it is. I think it's 2.65 meters, the same as Yao, but I think his salary, his contract was more expensive than the arm itself, so we went for the robotic variety, about the same reach, probably a little more sturdy under Martian conditions. And I'm sorry, the reason it's so long, originally the reason it's long is we thought we might have to dig way down to get the ice. Now we know the ice is probably this far from the surface, but it still helps us because it means we can dig here and dig there and dig there and take advantage of that reach to sample different places. At the end of that arm ignore the TECP for the moment, I'll come back to that, is the scoop that scoops up the dirt. It has all these funny little blades and scrapers because this is, I don't know if any of you ever tried to dig permafrost. Living in Southern California, I know most of you probably have, but nonetheless, it's really incredibly hard stuff to cut. So we have scrapers, we have diggers, we have this thing called a rasp that's, it's a Dremel tool. It actually is a Dremel tool bit that turns round and round and grinds up. A Dremel tool, a little grinder. These things you buy at the Ace Hardware that spin around and grind things. So it's a little grinder. It's going to grind the ice up, the icy soil, throw it in the scoop, and then we can drop it in the various instruments. That's what it looks like up close, grinding some icy soil in a test. Okay. Now, there's also this thing called planetary protection, which is a really weird idea. And there's two parts of this idea. One is that we should be really super careful about bringing anything alive, like little germs, to Mars or anywhere in the solar system. And the other half of it is we should be really, really careful about bringing any germs from other planets back to Earth, and we all can imagine why. In this case, that's not a problem because Phoenix, like all of our Mars missions to date, does not come back. But we do have to worry about contaminating Mars, and it's not even so much because we think that Mars will be overtaken by a plague that's going to kill all the native life, as we don't want the next mission to Mars to come back and say, my goodness, we discovered life, there's microbes all over this place, and find out that we brought them, the Phoenix brought them, okay? So we do a lot of very careful protection, particularly of the pieces that touch the ground and touch the ice. And that means we super clean this arm and we put it inside this bag that has a little motor that opens it up when we get to Mars. It's called a biobarrier. Now, in addition, we're doing experiments to look for organic molecules that might be in the Martian soil. How do you know you didn't bring those? It doesn't take germs. It doesn't take microbes to bring schmutz, to bring organics. So what we do is we put something really, really clean inside, a chunk of ceramic that we call a blank. And when we get to Mars, we'll open this thing up. That blank will be super clean. We'll take the rasp, we'll dig some up, we'll put it through all the instruments and say, this is the cleanest anything can be on Mars. If anything has a lot more organics than that, they probably were on Mars when we landed. If it has less organics than that, they're just stuff we brought along. So that's what's inside the biobarrier. This is the Tega instrument. It has 8 little cells that can be used once. Now, you saw in the previous picture the robot arm dropping soil into these things. First, a little door has to open. The little door opens, you dump the soil. There's a little vibrating kind of conveyor belt that brings it inside. The door closes up tight, and then you slowly heat this thing up to as close to 1,000 degrees centigrade as you can get, very, very slowly in individual stages. Well, there's 2 reasons we do that. Some of you may have done experiments in school, some of you may be doing them now, where you apply heat to, say, a pan of ice. You put a Bunsen burner under a beaker of ice, and you measure the temperature over time, and you see the temperature goes from -10 slowly up to 0, and it stays at 0 for a while the ice melts, and when it goes through a phase transition, and then it goes up again. Now, there are lots of phase transitions. This instrument does the same thing because as it heats it up, it's applying constant power, and it's carefully measuring the temperature at every step. So if it finds ice, if it finds clay, if it finds other different ways that volatile materials are bound up in that soil, we'll know it simply from that temperature profile. In addition, whatever gases come out of this go into a mass spectrometer. And the mass spectrometer can tell you the gases that were buried in that soil, including all those organics. So that's how we look for the organics, by heating this thing up to a ridiculous temperature and then sniffing for it with this mass spectrometer. Now, I'm going to spend a little more time talking about Mecha than all the other instruments because this is my baby. I've been living with this for 10 years. 10 years ago, next week, was the anniversary of what? Okay, a ringer, Lori. What was the anniversary? Pathfinder lander, which opened a whole new chapter in Mars exploration. And I'll never forget the year that followed because it was really when I got involved with Mars and spent a year creating, with a team of people, of course, creating and really selling this instrument to the program as an instrument that should be used to characterize soil on Mars, and it became part of the 2001 Mars Surveyor lander, the one that was eventually canceled. And it was an unforgettable year. And from the landing of Pathfinder to the next July 4th, before we were really going and starting to build an instrument for Mars. It's a suite of instruments. It's kind of a laboratory that does more or less what you would do if you were moving into a new house and you wanted to know if you could plant a garden in your backyard. You want to send a soil sample to the chemical laboratory, maybe look at it under a microscope, understand the geology, what kind of rocks made up that soil. So it has three parts. One part are all these little wet chemistry cells. These do the chemistry experiment where you take a little soil, you mix a little water, you make a little mud, you stick a pH meter in there, you drop in some chemicals and watch what happens. Just what you do in Chemistry 101. Incredibly difficult to do that without somebody stirring it and mixing in the chemicals. So all these little things stuffed into this is more or less a 3-inch cube. Incredible amount of little gadgets and sensors stuffed into that little cube. Each one of them can take one soil sample, and there are 4 of them lined up on the side. The dirt goes in here in the funnel. A little drawer comes out at the same time. The dirt falls into the drawer brings the dirt back in, and that starts the sequence. This is a microscope, and yes, I know it's lying on its side. Normally microscopes look down. This one is not looking down, it's looking sideways, because normally you also prepare a sample for the microscope. You get a slide. If you're looking at dirt, you'll sprinkle a little dirt on it, make sure there's not too much. You put a cover slip on it, and you'll slide it under the microscope, and you'll look down. If we did that in Mars, we'd just get a big pile of dirt. So instead, what we do is we essentially put the sample sideways. So, you know how hard it is to clean windows. Stuff always sticks to it. So essentially, we're dumping dirt at the top of this wheel. We're rotating it around to the bottom so it's standing up, and we're just studying the stuff that's clinging, that's staying behind. And that's why the microscope is on its side. And finally, we have this thing, which I said don't pay any attention to on the end of the robot arm. These are 4 little needles that get stuck in the ground, and they measure the property of the soils. And I have better pictures of these things. So this is that chemistry cell. Down here in this black box on the bottom, this is the proverbial black box you're always hearing about. It has all kinds of sensors for pH, for anions and cations. That means things like calcium, magnesium, potassium, sodium, chloride, iodide, bromide, sulfate, things like that. This is the stuff that allows you to fill it up with dirt. This tank back here is full of water that we bring from Earth, and we designed it sort of like a Coca-Cola can that you puncture it when you're ready and it all pours out. This is a little gadget that draws, we call this a Pez dispenser, not in writing because we'd get sued, but it basically drops little, there's a little spring and a little pusher, and it drops little pellets down one at a time in the solution. And we do that because some experiments we need to do by adding acid or we add barium chloride as a way to measure sulfate, because barium chloride, some of you may have done this experiment, it's called a titration. The barium reacts with the sulfate and makes barium sulfate, which precipitates out of solution. So you watch the barium go down, and that tells you how much sulfate you have. So we do little chemistry experiments. We have a little tiny pressure sensor there. We have little heaters. This striped thing here is a heater, temperature sensors, all that kind of stuff. And of course, you need a little spoon to stir it up, so we have a little stirring motor, and we control all this out of a computer. So that's the chemistry experiment. This is the TECP, the Thermal and Electrical Conductivity Probe. It's kind of like a Swiss Army knife. You stick it into the ground with the arm. It measures the temperature of the ground as it changes during the day and night. Measures the thermal conductivity of the ground. How well does it conduct heat, which is a way of measuring how much ice is in it. The icier the soil, the more it will conduct heat. Same thing with heat capacity. The icier the soil, the more heat it can hold. Electrical conductivity. If any of that ice starts to melt, it will become very electrically conducting. And starts to melt doesn't mean it's wet or it's damp. Even before it gets wet and damp, it starts to conduct electricity because the molecules are starting to wander around a little bit, even if they're not truly liquid. The dielectric properties, that's another measure of how much water might be in there. And there's a sensor that measures humidity in the air, so we can tell if water's coming in and out of the soil. And we discovered, to our delight, quite accidentally, after we designed this, that if you stick it up in the air and do the the thermal conductivity experiment, what you're measuring how fast the needles cool off, so you're measuring the wind speed. So we discovered we can stick it up in the air and measure wind speed, and of course use the same thing that measures the temperature of the soil can measure the temperature of the air. So it really, this little thing does everything. I described the microscope. What I didn't describe is how you pour the dirt in, this little chute in the cover, and it gets on a few of these little substrates here. These are all different, these little things that look like little tiny circles. They're 3 millimeters across. They have magnets in them. They have, various material. They have sticky, like silicone in them. They have some micro-machined little textured substrates, all kinds of stuff to hold on to dirt. So when we roll it down to the bottom in front of the microscope, there's dirt clinging to it of different kinds. And I always call it dirt, by the way, because planetary scientists don't like you to say soil, because soil implies that there's things living in it. And I don't like to go around saying regolith, which sounds really pretentious, so I say dirt. This thing here is an atomic force microscope, this little tiny thing, and it feels the shape of particles that are too small to even see with the best optical microscope. It's a little tiny thing, and it's all microfabricated. It's an experiment. It may work. It's obviously very delicate to try to do these things so far, 100 million miles away from your laboratory. But we're going to try it. It's a very clever little gadget. So I'll just walk you through how this thing works. This is that sample wheel that sticks out of the side of through that little slot in the side of the enclosure. The scoop comes along, dumps dirt on it, and then most of the dirt is scraped off by a blade, leaving just a little bit behind. You then roll it around so it goes in front of the optical microscope, which then takes a picture. And it's going to take a color picture because it has red and green and blue lights. That's not normally how we take a color picture. Usually we have color filters on your camera, but in this case we take a picture with a red light on, with a green light on, with a blue light on, and we combine them to make a color picture. Then we have this little AFM I mentioned, the atomic force microscope. You go even closer until it touches, and then you scan it and go back and forth. And this little picture is, I think it's 20 microns on a side, and you see all these little tiny features. If we saw something like that, we would get really, really excited, because that's a picture of diatomaceous Earth, which is little fossils all over the place. We don't expect to see them, but if any people ask what it would look like if we saw life on Mars with the atomic force microscope, it might look something like that. That's Mecha. That's my baby. The other instruments, there are a number of other instruments on Phoenix to take pictures other than our microscope. And to go from the biggest to the smallest, this is the camera that takes pictures as we come down to the ground. Right now we may think it may just take one picture, but that's all we need. One picture right before we land so we can see our landing site really up close and personal. The robot arm camera I described, it's like the Mecha Microscope. In fact, as far as the spacecraft's concerned, it's exactly the same as the Mecha Microscope. There's channel 1 and channel 2. Channel 1 is the rack. Channel 2 is Mecha Microscope. It has lights. They're LEDs. They're red and green and blue LEDs to illuminate the sample and the scoop. And it kind of sees things similar to what the MER so-called microscopic imager sees. So there's a terminology issue. We call it a camera. It's more like a magnifying glass. It's not like a microscope. And this is the workhorse. This is the cute one with the eyes and the mouth. That's a stereo imager with lots of filters. It can take really high precision sort of spectroscopic images. The big panoramas you're going to see on these walls after we're done of the first icy terrain we've looked at in Mars will be taken with this picture, with this camera, and you put on the little red and blue glasses and see all the terrain in 3D. So this goes up in a mast so that it can look a little bit over the horizon, and it pops up and shakes and shimmies and settles on the top of the mast where we can point it at things. The meteorological instruments, the weather instruments, came from Canada. And sometimes you have very little resources and you make do. The Telltale is a case like that. It was a last-minute addition. We didn't have a good way to measure the wind, and people kept saying, can't you just do what sailors do and you tie a little piece of yarn to the top of your mast, they call it a telltale, and take a picture of it? And we did. We actually did. Of course, it's not quite a piece of yarn, and the mounting had to be just right so it would survive launch. And it's special, what is it, Kevlar, Laurie? What's the Kevlar fiber with a little weight on the end. And it does blow around in the Martian wind, and we take pictures of it with the SSI imager that I just showed you, the stereospectroscopic imager. This is a little temperature sensor, just a little thermometer. It has to be very tiny because we don't want to measure the temperature of the temperature sensor sitting in the sun. We want to measure the temperature of the air. So it has to be very, very fine wires. And I guess this is the LiDAR that sends the laser up into the air and measures the clouds going by. So what are we doing? What's the plan? I mentioned we're going to land up above the Arctic Circle. They don't call it that on Mars, but I don't know what they call it. Usually people call it that thing that we would call the Arctic Circle if we were on Earth. We'll operate around 90 days through the summer solstice, use the robot arm to dig up dirt, analyze the icy samples and the soil samples with Mecha and Tega. We'll monitor the meteorology, especially the humidity, and we'll take lots of pictures as we go, because they fill in all the gaps in our knowledge that the analytical instruments can't quite tell us. The landing site, I had all these great pictures. Leslie Tamppari was originally going to give this talk, and she collected all these wonderful pictures of the landing site that she put on a Macintosh, and I can't read on my PC. So we can go to Mars, right? But we can't transfer files from a Mac to a PC yet. That's beyond our technology. I'll give you the basics. I'll give you the basics. You know, there's two groups that work on these landing site things. There's the scientists who say, I need to go, obviously, where I can get ice and soil. I need to go places where there's evidence that ice has done interesting things over the years, and what that really means is this so-called Peri-Glacial Terrain with all the polygons, the polygonal cracks that you see on Earth in cold, icy places, the ground cracks in these polygonal shapes. We want to go to a place that has that. We want to go to this high latitude where we know there's ice under the ground. Okay, those are our science requirements. And then the engineers come along and say, you can't go to like almost all of those. This one's too high, this one's too, well, they don't say this one's too low, this one's too steep, this one has too many rocks, this one has a crater in it. And because we kind of, Mars is pretty darn far away to kind of shoot a rocket and have it land exactly where you want. We need a pretty big so-called landing ellipse to aim for. In this case, 150 by 30 kilometers. We say, okay, we're going to land somewhere in there. Is that whole area safe, or 95% of it safe to land? Now, the history of trying to pick these sites goes way back to Viking. That was the first time we did this on another planet. And so Viking, we were a bit more careful. We knew we didn't have very good pictures of the ground. So we did it the expensive way. Of course, Viking, we did everything the expensive way. And we went into orbit first. And the idea with Viking, I don't know if you remember, when it was supposed to land. It was supposed to land on the 4th of July, 1976, which was the bicentennial. What a phenomenal way to celebrate the bicentennial, but to land a spacecraft on another planet in the solar system. How far we've come in 200 years. Well, they got up there, and they looked at the pictures of the landing site they had previously picked out, and they said, oh, darn, or something like that, something like that. I don't remember the exact word they used. It was something like that. Because it was, once they were at orbit and they could see pretty good pictures, it was strewn with rocks. They said, we can't land there, it's not safe. And they spent 2 more weeks. They missed all the news coverage, all the big bicentennial events. A couple of weeks later, they finally found a site that said, that's the place. And they went and they landed, and there were 2 Vikings, Viking Lander 1 and 2. Viking 2 gets down to the surface, and just as you've seen, say, with Pathfinder and MER, everyone's waiting, and there's finally the first picture rolls in, and you expect an enormous cheer, and people look at all the rocks all around the lander, and they said, oh darn, one more time. Somehow they landed safely in a field strewn with rocks. And I'm telling that story because that story never ends. We have beautiful, beautiful pictures of the landing site. Except now we have the so-called high-rise camera on the MRO instrument. And high-rise gives you resolution. You can see something this big. This is like, when you go to Google Maps and you look at your street and you see the cars on your street. This is kind of what high-rise will do for us. And so now we can really look for rocks. And so we had our landing site all picked out. These are the pictures from orbit. It's great. There's all these cracks we're interested in. There's no craters in these big areas. It's nice and flat. And you can download these pictures from the web. There's a special tool for looking at them. But you find you can blow them up and blow them up and blow them up, and there's still more stuff there. There's still more detail. The file that Leslie gave me with this pictures in it was 150 megabytes, and I shrunk it down to 6 just to fit these pictures in. They're huge. So, of course, there's a whole team of people all over the world analyzing these things. We're all set to go with our landing site for next year. And then Peter Smith, the PI, gets this little surprise email from someone on the high-rise team showing us the landing site we had picked out. And, of course, it was on Halloween. It was an appropriate Halloween surprise. Yes, all those things are boulders. Once again, we looked up close, strewn with boulders. And you can kind of go back and say, now that I really look, you see those little kind of dark fields over here? Yeah, up here, those are all boulders. So we started all over again. Again, we have a big area we can land in. We started with Region A and Region B and Region C and Region D, which they now call Dogbone, just because it starts with D. And so by Thanksgiving, from Halloween to New Year's, we went from that picture to this picture, and we got this greeting card for Happy New Year 2007. All this cracked terrain, no rocks in sight, and that's where we're going. So that's the landing site story from Viking to Phoenix. We expect it'll look, except for all the rocks, something like this. These are trenches that were dug in the dry valleys in Antarctica by Mike Mellon, who's a co-I in our team. And the point is, you dig up all this loose stuff easily with a shovel, and that's as far as you go, because this is ice, and you just can't dent that stuff without a pick. So we expect to find something like that, dry soil on top of this icy layer. And that's, of course, why we go to places like this, to try to figure out what we should be prepared for. We launch August 3rd. I still can't believe it. It's right upon us. One of the cruel jokes of this mission is that we're launching in August, we land in May, and that means that the team gets to spend August in Florida and next summer in Tucson. Studying this cold, icy place. We're looking at ice cubes in the pictures and saying, wish we were there. That's the Delta II launch vehicle that we'll be launching off of. Everyone should come and see the launch. You can stand on the beach with us. What's the time? 7:50. I might just skip this. I was going to talk a little bit about, the flavor of how this goes, but I think I'm going to skip it and roll the video. So if you want to ask questions later about some of the ins and outs and the details of building it, I'd be happy to answer them. I'm just filling time while you're rolling the video, right? Rolling the video. We don't have sound in this video yet, but because we usually need copyrights for the songs. That was the cruise stage being ejected. Now, the heat shield is generating a tremendous amount of heat. It looks just like if it was coming into Earth. You're generating just as much heat. You're just going faster till the atmosphere slows you down. The chute pops out. It's just like a chute you'd use on Earth, maybe a bit bigger. This is how it's supposed to work, a nice gentle fall, a little bit of rocking. And then the chute lets, the back shell comes off, the legs pop out. That was the point at which we think the mistake happened in Polar Lander, that when the legs came out, they tripped the landing sensors, and so these engines shut off too soon. And this last part with Polar Lander, we think, was falling. And as you can see, those jets blow all the dirt off the ground we were hoping to study. We're hoping that doesn't happen, but some of us are a bit worried about it. And yeah, these things, of course, it doesn't happen nearly this fast. This probably takes 15 minutes for each of these Chinese fans to open. Those are our solar panels, so we do those first, because if without those, we don't have power to do the rest. Yes, it really does that. It really does that. And this is the biobarrier I talked about. That pops open, and that kind of pops open pretty fast because it's on pyros. Laurie could probably tell you how long it takes. This is going to be really, really slow again, at least the first bunch of times we do it. That's the robot arm opening up. That's the scoop. It's turning around. It's going to go out. And this is days later, by the way, because we've been checking out all our systems for a few days. And that'll go down eventually and dig and bring dirt into the instruments just like this. It'll dig up some of the loose surface soil first. That's probably closer to the speed that it moves. And where's it? It's going in Tega first. That's Tega. This is Mecha in the front. More likely, this will be really fine, dirty stuff, like talc kind of fine powders. That's the laser I was talking about shooting up into the sky. You can see the clouds up here. The sun, it'll be like the Arctic in the summer. The sun will move around the horizon. And we'll do that for 90 days. I'm going to stop there because I'm looking at the time and I do want to have time for questions. So thank you very much. And I'm happy to stay and answer questions as long as you're willing to stay around and ask them. Yes?
All those nice cracks. Aren't they about as bad as boulders to land on?
We've talked a lot about that. And in part, the answer is they just cover a very small fraction of the area. There is a risk if we land in those cracks that we could land at a tilt that's unacceptable. That's the only reason we do it is because we think we can do it is because it's 5% chance or less. I don't know the exact number. Way in the back.
Where is it launching?
We're launching from Cape Canaveral in Florida. So if you come down in August, you can go to Disney World and go to Orlando. Your parents will be happy to take you. Yes?
What keeps you from bringing it up again for a second summer?
Well, a number of things are expected to break down in the winter. I think the first one would probably be the batteries. I'm not the expert on this, but that's my understanding. The batteries just won't survive. Yes?
I heard that the polar lander, the one that crashed, was going to have a microphone on it to listen to the wind. Does this too?
This does have a microphone. I'm not quite sure yet what we'll be doing with it. It's part of that descent imager. And there's some technical details about whether or not we can use it at the surface. I don't know if they've been solved. Is there any other Phoenix people in the room that have a better answer than that? We've all been excited about being able to do a microphone mission someday. It's also very useful to listen as we land, both in terms of understanding the winds, but also as some diagnostics on the spacecraft. Again, way in the back.
Can the solar panels be tilted toward the sun? Because it looks like an extreme incidence angle.
It is, and they cannot be. Every time you add a mechanism, there's a chance of something going wrong. And it turns out there's enough dust in the atmosphere in Mars, there's enough scattered light, that you get quite a bit of light on the flat ones. If you tilted it in one direction or another, it would work part of the day, but then it would be a lot worse the rest of the day. So we decided on flat so we get more or less uniform power wherever the sun is. Also, you can't always control exactly the angle you land at. Yes?
Why can't the ice be on the surface? Why does it have to be, why do you have to dig down to get to it?
Well, that comes out of some thermal models, but the short answer is that when it briefly warms up on the surface, it would evaporate. And it evaporate or sublimates much faster than it comes back down. It's like you defrost your freezer, once a month. That's all you have to do. It takes a very long time for the water to come back and build up again in the coils. Every time it gets warm in Mars, you're defrosting that top layer. Now, underneath that layer, just like on Earth, when you dig down, you'll get a part that never gets warm. Okay, so the ice just accumulates there and never comes off. So that's how Bruce Murray back in '66 could do a pretty good calculation of just where the ice was going to be. Because you guess at the thermal conductivity of the soil, one of the things we want to measure. You say how far, at the top, the soil on the top, the temperature every day is going hot and cold and hot and cold. If you go down this far, it's pretty much uniform, and that's where the ice will stay. When you get farther south, it gets warm enough, just like on Earth, that the ice is never stable there, and that's why south of 50, it's always sort of too warm. And by too warm, I mean it's above the frost point. So the ice doesn't want to stay there. In the purple shirt?
Early in your talk, you said that it's fairly well accepted that billions of years ago there was lots of water on Mars. Where did it come from and where did it go?
Well, it's most likely it's all still there in the form of ice. A quarter of the planet is covered with these ice sheets. We don't know how deep they go. We just know they start about here. So in terms of where it went, as I said, it's like a desert. It's just gone to the cold places and left the warm places. Where did it come from? You know, even on Earth, we don't know the answer to that question. There's people that think it was just always there as part of the ingredients of the Earth, and there are people that think that when the impact happened to Earth that created the moon, that all the water disappeared, and then it came back from comet impacts. As comets crashed on the Earth, it made water. It made all the oceans. You can make the same arguments about Mars because the early solar system was a very busy place and a very dangerous place. Yes?
What kind of fuel is used for the final descent?
It's
How does
hydrazine.
that contaminate the surface?
We are very worried about that. It's hydrazine. It makes various byproducts that may have ammonia in them. We've studied it. We've done the best we can to eliminate it. The Mecha chemistry cells, for example, have ammonia sensors so that we can detect the contamination, but the sad part is that it makes it difficult for us to look for nitrogen compounds that we don't expect to find, but it would be very exciting if we did because they're very important for life. So yes, we will expect to get some contamination. And if we were to have wheels, that would be one of the main reasons, so we can move away from that contamination plume. Yes?
Is the soil collection process completely automated, or is there any manual interaction there?
Well, manual interaction in the sense that, and this is what's so hard about operating these missions, in the sense that once a day you send commands. And it's all you can do. And it's not really a very smart robot in the sense it's not going to innovate if something goes wrong. It will pretty much stop. If it doesn't find what it expected, if it hits a rock or something makes the motor stall, it's just going to stop, phone home, and say, what do I do next? Way in the back.
How deep can Phoenix dig?
Well, if the ground is soft enough, remember Yao Ming and his long arm, the arm is about 2.5 yards long, but it starts about a yard above the ground. So it could probably dig about 4 feet down into the ground, right below the edge. Over here.
The descent imager, does it have any capability of changing the landing, moving side to side, or any feedbacks of it itself can direct its own landing?
We sort of did that on MER. We are not in Phoenix. This is just to take pictures. We're using radar for landing.
Does the radar feedback so it can adjust or not?
Yes, the radar does some. We're not flying. We're not going to pick targets with the radar, no. So we're not doing hazard avoidance. All the radar is doing is telling us when, where the ground is and when we're not moving relative to the ground. That's the main job, because if you land like this, you'll topple over. So we have to neutralize that horizontal velocity. That's the main job for the radar. Yes?
Is there any expectation to see a lot of layering visually and to look how far back maybe into the climate over the years?
That would be enormously, enormously exciting. I personally think that to do that, we have to dig really down into the ice, and all we can do is, as they say, scrape the surface. So if we saw signs like that, they would be subtle. You might see some change in the chemical composition right below the surface, for example. We'll certainly look for that. It would be tremendously exciting. Right here.
Does the spacecraft, does the lander communicate with Earth directly or through an orbiter?
Through an orbiter. And we're used to seeing, I showed you those gorgeous high-rise pictures of the landing site that have megabytes and megabytes and megabytes of data. We get terabytes back from these orbiters. From the lander, I keep pointing out that all the data we'll get from the lander from this whole mission, you'll be able to carry around on a thumb drive hanging around your neck. It goes through the relay, and so it's a very slow process. The way the orbital spacecraft work is that they go over the poles like this, and the planet turns like this underneath them, and that way over the course of many orbits you'll see the whole surface. Now we're up near the pole, and that's a good thing, so it means that all these orbital spacecraft will go overhead fairly often. And we have to, when they go overhead, we have 5 or 10 minutes to transmit data up to them. It's like talking on your cell phone. Just transmit data up to them at a low data rate, and these orbiters accumulate it and send it back to Earth. And it's barely a blip in the data coming back from the orbiters.
So it's not just one orbiter. The lander communicates with several of the orbiters.
It can communicate with several.
There are, what, 3 up there now?
Oh, right now we have, well, I think the plans would be to talk to MRO and to talk to Odyssey. I believe all the orbiters are compatible, which means there's the European Mars Express up there that I think may be able to work as a relay. Of course, we lost MGS earlier this year, and MGS was an important relay for MER for a while. So we have 3, at least two that we plan to use on a regular basis. Yes?
What's your launch window in August?
August 3rd to something like the 22nd. If we miss that, there's probably another opportunity in 10 or 12 years that will get us back to the pole in the summer. So we're not missing that one. Yes?
You mentioned that you want to know if the water ever is liquid. What about the things that you find would tell you that it was once liquid?
Right.
Well, there may be, in some cases, just the structure of the ice itself. It may well be the chemistry of the soil. There's certain kinds of geology that takes place when water is present and not when it's not present. It can be sometimes the shape of the particle grains when we look through the microscope that I've been told by people that specialize in studying particles of things, that study aeolian processes. You know, I've known particle physicists who study part of the kind of particles you hold in your hand, you know, not the kind your hand is made of. They study these things. They say, show me one particle, one grain of sand, and I can tell you its history. Okay, so it's a combination of chemistry. It's a combination of the shapes and the sizes. Yes?
What dictates whether they do a balloon landing like they did with the rovers or a rocket landing of this spacecraft?
There's a lot of considerations. In our case, we picked the spacecraft because it was in a box. This is heritage from Viking. It looks a lot like Viking. It's sort of the mini-me of the Viking series, made by the Lockheed Martin Corporation, and Martin Marietta built the Viking spacecraft. The Airbag Landers, Pathfinder was the first successful one. The Russians have used that similar technology for years. Have the advantage that they're more resilient with respect to hazards. You know, they can hit a rock and bounce off. But they're also very difficult to land. They're not very sensitive, say, to lateral movement. And they scrape very badly. So it's not, they each have their strengths and weaknesses for landing. The airbags tend not to carry very large payloads. So if you want to carry a lot of instruments, you're better off with a lander with legs. A lot of factors. Again, way in the back.
How are you planning to land this time without having the engine blow the dirt away from the...
How are we planning to land without having the engines blow the dirt away? Yeah. We're going to cross our fingers. We just have to live with that and study what we find. Right here.
Do you expect the ice to contain salt similar to the Earth's oceans?
We certainly expect the soil to contain salts because while we don't have something that directly measures salts, the MER instrument, the Viking instruments, have instruments that measure the elements that are in the soil, and there's lots of elements that suggest salts. Or there's lots of pictures that suggest minerals that suggest salts. You know, those very whitish features you saw, you know, right when Opportunity landed, you know, our magnesium salt, magnesium sulfate salts like that. So we expect a lot of salts in the soil. And one question, did they come out of the water when it dried up? That's one of the things we'd hope to learn. Yes?
Is it possible for the descent engines to heat up the soil enough to actually melt some of the ice while the lander is landing?
No, that's much too quick, and boy, it takes a lot of heat to melt ice, an awful lot of heat. So we don't expect that to be a problem at all. Right here.
Can you say anything about any other Mars missions in the near future?
The next big and exciting Mars mission is the MSL, the Mars Science Laboratory, which I've heard sort of tongue-in-cheek described as MER on steroids. It's a great big rover with a radioisotope thermoelectric generator like Viking had. So it's a radioactive source, so it can keep going and going and going and doesn't need sunlight. Very different kind of instruments. The instruments on MER were geology instruments. They were instruments for looking at rocks primarily, and they could grind the rock and take a picture of it and do Mossbauer spectroscopy to look for iron. With MER, the instruments will be more oriented toward looking for organics, looking at crystallography. There's some radiation environment experiments on it. There's very different kinds of instruments and an emphasis on going for a long time and long distances compared to MER. After that, the mission. There's been another so-called Scout mission, a low-cost mission that's been selected for 2011. That will be an orbiter, a so-called aeronomy mission that's going to study the upper atmosphere. And after that, I could tell you, but it will change before they do it. Right here, where we started.
What's the maximum tilt you can land on?
The spacecraft is designed, our marching orders are, we should be able to tolerate up to 16.7 degrees. I don't know why 16.7. And it's the same lander that we had in 01, and the number changed by a little fraction of a degree. Now, that doesn't mean we will give up if we land on 25. But it means it hasn't been tested beyond that 16 or 17. Yes?
What's the communication data rate from Phoenix?
When we're actually running for those 5 or 10 minutes per orbit per pass, which might happen a couple of times a day, it'll go up to typically 128 kilobits per second. It's slow. I think MER, if I'm not mistaken, got up to 256 on some of their transmissions. But it's we're talking 1,500 megabits a day, bits a day. It's not very much. Yes?
Obviously, there's so many things that you could study. When you're planning a mission, how do you narrow the field of, okay, we're going to study this and study
That's a wonderful question. And the way it works is that, say in this case, for this mission, there were 18 different groups of people who knew exactly what they wanted to study and spent enormous chunks of their lives writing proposals, trying to convince NASA which one. Now, how was the selection made? It was made by about 100 people reading each of these proposals. Some of them reading them were scientists who said, is this an important thing to study? Will it get back the science answers that it's supposed to get back in an unambiguous way? We have the right people leading it. A lot of them are engineers saying, is this going to work? Will it fit within the budget? Are they going to run into trouble? Are the instruments going to work? So that's the process. It's a competitive proposal process, and it's grassroots in terms of what the ideas are. Now, that's in a mission like Phoenix, or this aeronomy mission I mentioned. The missions like MSL are a little different because a panel of scientists says, we want a mission that's going to be a big rover that's going to go in this area and have these capabilities. And then we go through the same thing, proposing the instruments and the experiments. So sometimes we propose the whole mission. Phoenix was competing, for example, with a mission that wanted to scoop down, to dive into the atmosphere, get samples of the air, and come back out and take them back to Earth. That was one of the competitors. There was another competitor to fly an airplane through the, and it's close to the surface of Mars, and take pictures as the airplane skimmed the ground. So there can be all kinds of wild things proposed. And in the end, you narrow it down to something that looks like it's important and you can do. Yes?
Since this Phoenix is going to be a stationary place, not moving around, so it can do limited experiments. How long do you expect to be this project lasting?
We're limited by the weather. It's going to turn real cold after the first few months. So it's 90 days, and we'll be hard-pressed to do all the experiments we would like to do in 90 days because everything won't go perfectly. We know that. We might get another 30 days afterwards at low power to do maybe meteorology. Yes?
Now you have about 8 or so shots to get readings back on your instruments. How do you choose which samples you want to drop into the instruments?
Well, yeah, the Tega had 8 and the Mecha Chemistry had 4. The going in position is we want to sample the very top surface. We want to sample something below the surface that hasn't been bombarded with light, but is still dirt. We want to sample the top of the ice, where you actually grind some ice. And after that, we're frankly just going to sit around and argue about it a whole lot. And we're going to be in Tucson in the summer. There's not going to be much else to do. Yes?
Are they still planning a sample return mission?
Yeah. Yes, with the sample return mission has always been very, very high priority, but it's always been out of reach. And it's very much something that is in the long-range plans. I wouldn't even venture a guess when. Yes?
With a limited power budget, is it difficult to heat soil up to 1,000 degrees?
Yeah.
How are you going to do that?
Very, very tiny amounts of soil. We're talking about 30 milligrams, tiny fraction of a gram. The power budgets are just staggering. You forget. You get mired in the stuff and you forget what how little power you're talking about. we're talking about running an instrument. If I go to 30 watts on my instrument with all the electronics, I can't do that for very long, okay, because of the spacecraft budget. 30 watts, I mean, if we had a 30-watt light bulb, you wouldn't be able to see me. Okay, this is not much. In the back.
So, how much a percent is the chance that the mission will fail?
If I knew that. You know, I mean, all we can do is look historically at what we've done. We've lost the polar landers, the only lander we've lost. The Russians lost lots of landers. We've lost a couple of orbiters. We lost the Mars Climate Orbiter. Before that, we lost Mars Observer. So I'd say these days, most of them are successful. Maybe 3 out of 4 are successful in the past. And we'd like to think that we get smarter each time. A lot of the answer to the question I raised, why are these things so expensive? It's because we're building them so they won't fail. Each time we fail, we learn a very great deal. So I fully expect this will be a successful mission, and if it isn't, we will be very unlucky. Take one more, and then we should let people go.
What kind of arc can you swing that robot arm through? So, for example, could you take a sample here and a sample there?
The arm has 4 motors, 4 degrees of freedom. If you want to talk more about it afterwards, I suggest Lori Shiraishi here, who's the mastermind. But it has a shoulder that goes up and down and rotates this way, so you can pivot all the way around. And that's useful for getting, it's mounted at the edge of the deck, so you need that pivot so you can go over to the instruments. It has an elbow that goes like your elbow up and down. It doesn't twist, just goes up and down. And it has a wrist that goes up and down, knock, knock, like that. And that's it. So you've got those 4 degrees of freedom, and as I said, it's 2.6 meters long. Anything you can do with those motions, we can get to. Okay, and why don't I wish you all good night. I'll be happy to stay here if people want to come up and ask more questions. Thank you.